Okay, in this video we're going to be applying our knowledge of gradients to solving an actual practical problem. So suppose that water is being poured at a constant rate into an empty tank, and it takes 3 hours to fill it with 6,000 liters of water. And then what we want to find out is exactly at what rate we're actually pouring the water into the tank. So that's one of the main things that we would be interested in calculating here. And at first you might think, oh, that sounds very complicated. I don't really think I know how I would actually go about that. But there are two key words that we need to take into account here. And it is, we have a constant rate, which means that the rate at which we're filling in the tank is going to be a single value, and it's going to be the same for any time t. And then they're giving us a piece of information that it says it takes exactly 3 hours to fill in 6,000 liters. Now, what are the two variables that we need to actually model here? We have the volume of the tank and we have the time. All right, so that means that we should be able to actually model this as some sort of relationship between those two variables. So question A is asking, what is the rate of pouring? Well, think about it this way. You're starting off at originally at time 0. Actually, let me just write the V on this side. Let me just make a little table here. At time 0, right, the volume is 0 because the tank was empty. Then at 3 hours, the volume became 6,000. So that was how much water was into the tank after 3 hours. So based on those two pieces of information and the fact that the rate of filling is constant, then we should be able to calculate that simply by taking, as we have done before, the gradient between those 2 points. So imagine that each of these pairs is a point on the Cartesian plane. Then by simply doing what we have done before to calculate the gradient, we can find the rate. So let's call the rate r. So in this case we're gonna have r equals to, okay, so let's take, because we want to essentially have volume in terms of time, we're gonna assume that volume is going to go on the vertical axis. So we're gonna have something like this: 6,000 minus 0, and then we're gonna have 3 minus 0, and then 6,000 divided by 3, that's 2,000. Now in this case we're actually talking about a practical setting, and we're actually given units. So for example, time is in units of hours and volume is in units of liters. So in this case, if this is liters and this is hours, this would be liters per hour. Okay, so that would be the rate of filling that tank. Another way in which you could visualize this is by actually plotting this on a Cartesian plane like this. So we have t on the horizontal axis in hours, and then we have volume on the vertical axis in liters. So now what we can do is we can say, okay, so we're starting off at 0, then at time 3 hours we're going to go to 6,000 liters. Now, if the rate of filling is constant, then we should assume that this is going to be a straight line, because that's what a straight line is. It is a line that has a constant gradient. So in this case, we can draw a line that passes through both of those points, and that's going to give us the relationship between volume and time. Actually, this would be part B of the question because we already did it. So draw a graph of V versus t. Well, we just did it, so that's done. Now question C. Question C is going to be finding the equation for V. So let's see what we can infer from this. Well, we already know what the gradient is. So if we were to write V in terms of t, we can write RT plus some initial volume. Let's call it little v. And in this case, we notice, well, the y-intercept or the vertical intercept is at 0, so this term is just going to be 0, which means the equation of the line should just be rate times time. Okay, and we already know what that is, so we know that v is going to be equal to 2,000 times t based on that straight line that we just drew. And that sounds like a reasonable number, because if we plug in 3 hours here, we're going to get 6,000 liters. So this would be part C. That's the equation of that line. Okay, now the next part is question D. So we're asked to use the information we have already gathered to find the volume after 1.5 hours. So let's do that here. So question D, volume at t equals to 1.5. So we can just use the equation that we just derived in the previous step. So that's going to be V at 1.5. Well, we're just going to find that 2,000 times 1.5. That's going to come down to 3,000 liters. And we can check that, because if we draw a 1.5 here, that's going to take us halfway through, and then we should end up somewhere here. Okay, so we can if we draw the graph properly, we can always check our answers graphically. Now, part 2 of that question is going to be find the time to fill 5,000 liters. So in this case, we're going to do the opposite. We want to find out, okay, so if we are filling in 5,000 liters, then how much time would that correspond to? So in that case, what we're going to do is the reverse process. We're going to write V equals to 5,000, and that's going to be equal to 2,000 T, which implies that T is going to be 5,000 divided by 2,000, which is 5 on 2, or simply 2.5 hours. Or just 2.5 hours. There's still ways of writing that. It doesn't really matter, but you get the idea. So we have effectively modeled something that didn't seem like it could be modeled using a linear equation by simply using this concept of straight lines and using the gradient. So whenever you're talking about a rate of change, you're usually talking about a gradient. So you're talking about the gradient between 2 points, and those 2 points can usually be just values of how a variable is changing with respect to another. So hopefully this has shown you some of the applications of straight lines, and in the next few videos we're going to be doing more stuff with straight lines, and you'll see that it's actually quite useful to a lot of different areas.